Think about what happens in the first fraction of a second after a commercial airliner touches down. The main landing gear wheels, which had been stationary since the aircraft left the ground hours earlier, made contact with the runway surface while the aircraft is still moving at roughly 250 to 280 kilometers per hour. In that instant, each tire goes from zero rotational speed to full ground speed in less than 1 second. The rubber is scrubbing against concrete or asphalt under a vertical load that can exceed 20 metric tons per wheel. The temperature at the contact patch spikes almost instantaneously, and this happens on tires that are inflated to pressures between 12 and 20 times atmospheric pressure, containing enough stored energy that a catastrophic failure would be comparable to a small explosion. The question is not just why they survived this. The question is how they were designed to survive it repeatedly, thousands of times, across the entire service life of the tire. Start with the pressure. A typical passenger car tire runs at around 2.2 to 2.5 bar pressure. A bicycle tire runs at 5 to 9 bar. A main landing gear tire on a Boeing 737 is inflated to approximately 14 bar. On a Boeing 777, main gear tire pressure is around 15 to 16 bar. On the Airbus A380, with its 22 main gear wheels supporting a maximum takeoff weight of 575 metric tons, tire pressure reaches approximately 17 bar. These are not approximations, they are precisely controlled values that are part of the aircraft's weight and balance documentation. The reason for such high pressure is straightforward. The tire must support an enormous load on a contact patch that is deliberately kept small to minimize rolling resistance and aerodynamic drag from the wheel wells. Higher pressure means a stiffer tire, a smaller contact patch, and more load carried per unit area of rubber. The trade-off is that the stored energy in a high-pressure tire is enormous. A fully inflated 777 main gear tire contains enough energy in its compressed gas alone that a sudden failure would generate a pressure wave capable of causing serious structural damage to the surrounding airframe and landing gear components. This is precisely why aircraft tires are not filled with air, they are filled with nitrogen. The reason is not exotic, it is straightforward chemistry and physics. Atmospheric air contains approximately 21% oxygen. Oxygen supports combustion. During a hard landing or a rejected takeoff, brake temperatures on a heavily loaded aircraft can reach 900 to over 1,000 degrees Celsius. The landing gear bay and the wheel assembly are exposed to that heat. If a tire were to lose pressure rapidly in that environment, a mixture of hot oxygen and tire rubber vapor would create conditions that could support ignition. Nitrogen is an inert gas. It does not support combustion. Even in the presence of extreme heat and ruptured rubber, a nitrogen-filled tire that loses pressure does not contribute to a fire in the same way that an air-filled tire would. Additionally, nitrogen has a more stable pressure response to temperature changes than air because air contains water vapor that expands and contracts more dramatically with temperature swings. At the extreme cold of cruise altitude followed by the heat of braking, nitrogen maintains more consistent pressure throughout the flight cycle. The structural design of an aircraft tire is completely different from an automotive tire. An automotive tire is a relatively simple structure of rubber over fabric cords arranged in a radial pattern. An aircraft tire is a multi-layer composite structure engineered to handle loads and stresses that would destroy an automotive tire in a single cycle. The carcass of an aircraft tire consists of multiple plies of high-strength nylon cord fabric laid at specific angles and embedded in rubber compound. These cord plies carry the tensile loads generated by the internal pressure and the bending loads imposed during ground contact. The number of plies and their orientation determine the tire's load rating and its resistance to deformation under load. The tread compound is formulated specifically for the abrasion conditions of landing. At 270 kilometers per hour ground speed, the contact between a stationary tire and the runway surface during the initial spin-up generates frictional heat at a rate that would melt standard rubber compounds almost immediately. Aircraft tire rubber uses specially formulated compounds with high heat resistance, controlled hardness for grip, and the ability to resist the tearing and chunking that occurs when rubber is subjected to high shear forces at elevated temperatures. Even so, landing consumes measurable amounts of tread material. The characteristic puff of smoke and rubber dust visible at touchdown is not the tire overheating in a catastrophic sense. It is the controlled ablation of tread rubber that is expected and accounted for in the tire's service life. The spin-up itself, the transition from stationary to full rotational speed, is the most severe single event in the tire's load cycle. During this fraction of a second, the contact patch is experiencing sliding friction rather than rolling friction. The rubber is not rolling cleanly. It is scrubbing across the runway surface while the tire's rotational inertia resists acceleration. The heat generated is concentrated in the tread and the surface of the runway. On a dry runway, the scrub mark left by a landing aircraft, the black rubber deposit visible at the touchdown zone, is direct evidence of this event. On a wet runway, the water film provides some lubrication but introduces the risk of hydroplaning, a condition in which a film of water completely separates the tire from the runway surface, eliminating friction and making steering and braking impossible until the water film breaks down and contact is restored. After spin-up, once the tire is rolling at ground speed, the load regime changes. The tire is now carrying the full weight of the aircraft through rolling contact while the brakes are being applied. On a modern airliner, the braking system uses carbon-carbon composite brake discs and stators that can absorb enormous amounts of energy. The heat generated during a maximum energy stop, a scenario where a fully loaded aircraft accelerates to takeoff speed and then rejects the takeoff at the last possible moment, is so large that the brake assembly can reach temperatures where the carbon material begins to glow visibly. In this scenario, the tires are exposed to radiated heat from the brakes in addition to the frictional heat of braking contact with the runway. Fusible plugs are installed in the wheel rim to prevent exactly the failure mode that the pressure makes most dangerous. These plugs are designed to melt at a specific temperature, releasing the tire pressure in a controlled way before the internal pressure builds to a point where a catastrophic rupture occurs. A controlled deflation through a fusible plug is a survivable event. An uncontrolled explosive failure of a high-pressure tire is not. The wheel itself is a precision engineering component that is often overlooked in discussions of landing gear. Aircraft wheels are forged from high-strength aluminum alloy, typically a 2000 or 7000 series alloy with carefully controlled heat treatment to achieve the required combination of strength, toughness, and resistance to fatigue. The wheel is split into two halves, an inboard half and an outboard half, bolted together around the tire. This split construction is necessary because an aircraft tire cannot be mounted by stretching it over a wheel rim the way an automotive tire can. The bead of an aircraft tire, the reinforced edge that seals against the wheel rim, is too stiff and the tire too large to be mounted on a one-piece rim. The two-piece wheel allows the tire to be installed by assembling the wheel around it. The bolts that hold the two halves together are a critical structural element and are subject to strict torque specifications and inspection intervals. The landing gear structure that connects the wheels to the airframe is a hydraulically actuated mechanism that must retract into the fuselage or wing within seconds of liftoff and extend fully before landing. The geometry of the gear is designed so that the load path from the wheels to the airframe is primarily axial, meaning the loads pass through structural members in compression or tension rather than bending. Bending is the most weight-inefficient way to carry a load in a structure, and minimizing bending in the landing gear allows it to be lighter for a given load capacity. The shock absorber, called an oleo strut, is a hydraulic and pneumatic device that absorbs the vertical energy of touchdown by compressing oil through a calibrated orifice. The rate at which oil can flow through the orifice determines the stiffness of the strut, and therefore how quickly the vertical velocity of the aircraft is arrested at touchdown. A correctly serviced oleo strut extends and compresses smoothly over several inches during touchdown, preventing the sharp vertical impact from transmitting directly into the airframe structure. Tire maintenance on commercial aircraft follows a precisely defined inspection and replacement schedule. After each landing, the tires are visually inspected for cuts, bulges, tread wear, and any debris embedded in the tread. Tread depth is measured at regular intervals. Aircraft tires are retreaded, meaning the worn tread is removed and replaced with new rubber compound bonded to the existing carcass multiple times during their service life. A typical aircraft tire carcass can be retreaded 5 to 7 times before it is retired. Retreading is not a compromise. It is a standard and certified maintenance practice that maintains the structural integrity of the carcass while renewing the tread compound that does the actual work of absorbing landing loads and providing runway grip. The entire system, the nitrogen fill, the multiply composite carcass, the heat-resistant tread compound, the fusible pressure relief plugs, the split aluminum wheel, the oleo strut shock absorber, and the retreading maintenance program exist because the landing event is genuinely one of the most severe mechanical environments in all of transportation engineering. No other wheeled vehicle routinely experiences the combination of high speed, high load, instantaneous spin up from zero, and repeated thermal cycling that a commercial aircraft landing gear encounters multiple times per day across a service life measured in years. The tires do not explode because every aspect of the failure mode was anticipated during the design process, and a specific engineering solution was implemented to prevent each one. The smoke at touchdown is not a warning sign. It is evidence that the system is working exactly as designed, absorbing an extraordinary event within its engineered limits, ready to do it again on the next flight. Which leads to a question that follows naturally. If the tires and brakes are pushed this close to their limits during a normal landing, what happens during a rejected takeoff where a fully loaded aircraft at maximum weight must stop from takeoff speed on whatever runway remains? The energy involved exceeds a normal landing by a significant margin, and the engineering response to that scenario is one of the more demanding problems in commercial aviation design.